In this question it is given that the rate of steady volume water through capillary tube of length L and radius R under a pressure difference P is V. So it means that suppose if you are considering a tube through which some amount of liquid is flowing. So over here the dimensions of this tube is given. A steady volume flow of water through a capillary tube of length L and radius, let's say its radius is R, under a pressure difference P. Let's say the difference in pressure between ends is equal to nothing but P, is V. So this volume flow rate is represented as nothing but V. So we can write the equation for it, that is volume flow rate or dq by dt, or the value of V is equal to pi r raised to 4 delta P divided by 8 into eta into L. So we can write the volume flow rate is pi into r raised to 4 into delta P is given as nothing but P divided by 8 eta L. Now in the next part of question it is given that this tube is connected to another tube of same length but the half the radius in series. So now we are considering that this tube is connected with another tube of radius that is half the radius of initial one. So we can just take it as radius of this one is nothing but R and radius of this one is nothing but R by 2. And the rate of steady volume flow through is, so in this situation our aim is to find out what about the value of rate of flow of liquid through this arrangement. Assume that rate of flow of liquid through this arrangement is equal to V, and we are maintaining same pressure difference P across the ends of this tube, same as like in the previous case. So we can just consider that the pressure difference across the first tube is taken as delta P1, and the pressure difference across the second tube is taken as delta P2, or we can write the total pressure difference is nothing but P. So we can write delta P1 plus delta P2 is equal to the value of total pressure difference, which is equal to P, same as like in the previous case. Now we can identify what about the relation between this delta P1 and delta P2 over here. Now as these two tubes are connected in series, the same flow of liquid is going to happen between, same volume flow of liquid is going to happen between both the tubes. So we can write from that equation that volume flow rate or the value of dq by dt is equal to pi r raised to 4 into delta P divided by 8 eta L. So you can write what are the factors affecting this difference in pressure, that is equal to volume flow rate into 8 into eta L divided by pi r raised to 4. In both the situations the value of coefficient of viscosity, length, etc. and even volume flow rate is same. So we can write this delta P is inversely proportional to r raised to 4. So we can write delta P1 divided by delta P2 is equal to, we can take it as it is R2 divided by R1 raised to 4. And R2 is nothing but R divided by 2, and R1 we can take it as R raised to 4. So this is something like 1 by 16. So we can write the value of delta P2 is equal to 16 times of delta P1. Now already we wrote the relation that delta P1, that is pressure difference across the first tube, plus delta P2, that is pressure difference across the second tube, is a total pressure difference P, delta P, which is given as nothing but P. So we can write this as delta P1 plus delta P2 is 16 times of delta P1 is equal to nothing but P, or you can write 17 times of delta P1 is equal to P, or you can write this delta P1 is going to be P divided by 17. So we can find out what about the value of volume flow rate now. So let's say volume flow rate now is represented by V dash, and or the value of dq by dt. We know that the relation is pi into r raised to 4 delta P divided by 8 eta L. Now the value of delta P becomes equal to P divided by 17. So we can write this as 1 by 17 times of pi into r raised to 4 into delta P, which is P, same as like in the initial case, divided by 8 eta L. And the initial flow of liquid is given as nothing but volume flow rate is given as V. So now we can write the value of volume flow rate is V divided by 17.